Alright, so in this video we're going to discuss how to find the equivalent capacitance for capacitors in series and parallel. So an equivalent capacitance allows you to establish a capacitance for the whole circuit versus the individual capacitances of each capacitor. So we're finding the capacitance that is the combination of these two capacitors versus their individual capacitance. And we're going to discover that depending upon whether it's in series or whether it's in parallel, those values are different. And so sometimes you're going to want to use capacitors in series or capacitors in parallel in order to get the circuit to have the type of capacitance you want it to have. Alright, so we're going to start with capacitors in series. And when we have capacitors in series, the magnitude of the charge is the same on all the plates. And this is due to charge conservation. So remember, charge comes from a physical object. It's an excess of an electrons or a lack of electrons. So it's actual physical objects that are flowing. So since there is one path, the charge actually has to go from B to A. There's no other place for some of the electrons to wander off somewhere else. So that the charge here has to be the same as the charge here. And this is especially true because the charge comes from your power supply. So there is a power supply hooked up between A and B, and so the charge comes off of the power supply. It negatively charges this plate, which creates an electric field, and thus an electric force, which pushes charge off of this plate until they're equal. And that excess charge ends up here, so from this plate, to make it positive, the electrons end up over here, which in then turn does the exact same thing. Pushes the charge off of this plate so it flows back to the power supply. So that means because the electrons from this plate have to go to this plate, there's no other option for them, this charge and this charge is going to be equal to each other. So the charge on both capacitors is going to be the same. So if we look at our capacitance equations, remember capacitance is the ratio of Q to V. So based upon what power supply is hooked up between A and B, that's going to dictate how much charge we end up on each capacitor. I'm going to rearrange this to solve for voltage. So voltage is going to equal Q divided by C. Now, the voltage across, or potential across, these capacitors are going to be different. And so we often refer to these as items in a circuit as voltage drops. So it takes a certain amount of energy to get the electrons, for the electric field to push the electrons off of this plate onto this one. So you're losing energy in order to do that, to refer to a voltage drop. So when you get back to A, you have zero energy, which is why you need a power supply. But V1 plus V2, the voltage across this capacitor and this one, have to add up to the voltage from the power supply. And the charge is the same on both, so you would distribute it in to C1 and C2. So your rearranging this allows us to see that the equivalent capacitance is going to equal 1 over C1 plus 1 over C2. Now I've done this only for two capacitors, but if you had a third one in series, you could add a 1 over C3. I will advise you guys to be cautious with this formula, that this setup here solves for the inverse of the equivalent capacitance. So don't forget, when you do 1 over C1 plus 1 over C2, you then need to do the inverse of that to find the equivalent capacitance. If you just do 1 over C1 plus 1 over C2, you end up with the inverse of the equivalent capacitance. Alright, now for capacitors in parallel. So for capacitors in parallel, the potential difference across all the capacitors will be the same. And this is because the electric force is conservative, which means that it's path independent. So it's going to be the same amount of energy here versus the same amount of energy here, because it's path independent. Very similar to if you're trying to raise something a certain height, it takes the same amount of energy if you go up a ramp or if you go straight up in the air. As long as you're reaching the same height, it's the same amount of potential energy. It's the same here with the electric force. Whether you're taking this path or this path, it's the same amount of energy. What is different now is the charge, because now there's what we call a junction point, where the charge can flow here or it can flow here. And because, once again, charge is a physical object, as it comes out of the power supply, so I've been using B as the negative where it comes out, some of that charge that comes along here is going to go this way instead of it's going to go this way. You can't have 10 electrons here and then 10 here and 10 here. That means you've ended up with an extra 10 electrons out of nowhere. So depending upon what your power supply is and your capacitance is, you're going to end up with so many electrons here and so many electrons here, but it would have to add up to 10. All right, so once again, starting with our idea that capacitance is the ratio of Q to V, I rearranged this time to solve for Q. Now because, as I said before, these are physical objects, the charge that goes this way and the charge that goes this way has to add up together to what the Q was that came out of here. And that's going to equal our capacitances added together times the potential that's coming from the power supply. So this here, the C1 plus C2, is going to be our equivalent capacitance. So for capacitors in parallel, we're simply going to add the capacitances of the individual capacitors together to find the equivalent capacitance.